We've just learned about Gibbs free energy. Now, why is this in a chapter about electrochemistry? What is electrochemistry? Well, it turns out they're related to each other. But before we get to that, let's first describe what is electrochemistry. Electrochemistry is any chemical reaction that contains the transfer of electrons, right? So if the reactants, if something gives up an electron, another species takes that electron, we call this a redox reaction, and this now becomes electrochemistry, okay? And you've probably seen this, right? In movies, I'm a child of the 80s, so I grew up watching Aliens, right? And in Alien, they have this blood of the xenomorph that can just eat through everything. It's just this super corrosive acid. But in your lives, you've probably seen acids dissolve things. So let's dive into that and see what's going on there. Let's think about zinc metal in an acidic solution. So imagine this scenario. You've got a rod of zinc right here, and then you have this electrically conducted by a little piece of wire going down into this acid solution. So you can have the following things take place. The zinc metal gets dissolved, meaning it goes from zinc as a metal to turning into zinc 2+, which is now an aqueous ion in solution. At the same time, you've probably seen whenever something's bubbling, right? Even in this like xenomorph thing, you can kind of see that it's usually, sort of bubbling like there's a gas being evolved. That's often the case, and it's usually hydrogen being evolved, but it depends on what the solution is, right? So that's the same here. In this situation, we've got, say like a platinum wire. The platinum wire is in the solution, and then it's going to be generating hydrogen gas, okay? So gas gets evolved, right? And the zinc metal gets dissolved. So we could write this up into two what are called half-cell reactions, right? In the redox reaction, since something is giving up electrons and something is accepting electrons, there's two half cells that we need to worry about. So on one half, right, at the anode, we call it, we'll talk about why that is in a second, we have zinc metal, and it is turning into zinc 2+, and in order for it to go from zinc metal, which is neutrally charged, to zinc 2+, it has to give up 2 electrons, right? So these 2 electrons are now free to go somewhere else. On the other hand, at the cathode, right, that's where the hydrogen gas is being evolved, we've got acid, which is just H+ ions in solution, that's an acid. They're going to react with an electron to form half of a mole of H2 gas, right? We had to do half to make this chemically balanced. Now we could multiply that bottom equation by 2, right? We'll just do it 2 times over here. And that gives us, it becomes 2H plus ions plus 2 electrons yields 1 mole of H2 gas, okay? Now we could add these two reactions together. Remember, this is happening at the anode. That's what we call the anode, is where it's going to be giving up the electrons. And the other one is going to be at the cathode. That's where electrons are going to be accepted. Okay? So if we add those up, we combine those two reactions, we end up with the following. Zinc plus 2H plus 2 electrons will yield, we've got 2 electrons on this side as well, plus a zinc 2+ ion plus H2 gas. So you can see that right away our electrons cancel out. So oftentimes in these chemical reactions, you would just write zinc plus 2H plus gives zinc 2 plus an H2. You'd leave out the electrons, but I think it's important to remember that this is a redox reaction, and because we have these two half-cell reactions, there is an exchange of electrons, okay? So that's what's happening whenever you see metals getting dissolved, and this is an electrochemistry reaction because there's this exchange of electrons. Now, think about this though for a minute. When you take copper and zinc, you can also get a reaction, right? If you take one solution that's copper and one solution that's zinc, and you connect these electrically by putting a little wire between them. We would literally take a little wire and connect them. And then the next thing we have to do is we have to add a salt bridge, right? So you have to add some sort of bridge here. And inside of here, you've got a salt. Why do we use a salt? It just has to have both, it has both positive and negative ions, right? Why do we need that? Well, think about what's happening here. If you didn't have this salt bridge connecting these things, then as this reaction took place, the zinc would dissolve into zinc 2+. You'd start to accumulate a large positive charge here. Meanwhile, you've got these electrons coming over here. You'd start to accumulate large negative charge as the H+ gets turned into hydrogen gas. So you would build up a difference in voltage. You'd have a positive charge and a negative charge here, and it would eventually stop the reaction. You'd have, if you have a difference in charge, right, this would become positive, and this would become negative, and that would produce an electric field, which would resist electron motion. So basically your battery would work for just a moment and then it would stop. So you have to have something to get rid of those positive and negative charges. And you do that by bringing chloride ions this way and potassium ions this way. So remember, this was negative before, but the negative and the positive from the chlorine cancel out. This was positive before, but those cancel out. So that's the role of the salt bridge. So if we come down here and we've got our copper and zinc and we connect them electrically and then we connect a salt bridge, you will see the following take place. The zinc will start to get dissolved and the copper will start to have copper ions from solution precipitate onto your piece of copper metal. So we can actually see this happening in real life in the penny battery demo. So I put this video up on YouTube the other day. You can take a look at it. Essentially what's happening is pennies are made of zinc on the inside and they're just actually wrapped in copper. So if you file away the zinc on one side, now you've got a junction where copper and zinc are touching one another. If we apply a salt bridge like we do in this video, you're going to be able to generate a small voltage, and that's what we do. We generate a large enough voltage by stacking these things together, but check it out. 6 or 7 pennies stacked up. Now we take an LED, and you'll notice that it has enough voltage to light the LED up. All coming from the metal. How cool is that? So it can actually, just like we saw here, where you have this external circuit that the electrons travel through, the electrons travel that way. Well, that could be where your LED is, for example. And it provides enough electrical current that it can actually light an LED from this simple reaction of copper plating and zinc dissolving, that electrochemical reaction. Okay?